James Webb Telescope just found what scientists were afraid of, and the discovery is challenging the very foundation of our cosmic history. Deep in the ancient darkness where the first stars should be flickering into existence, the telescope has instead found massive, mature galaxies that simply should not be there. These are the impossible galaxies, giants of light, that formed in a window of time far too short for gravity to have finished its work. Astronomers expected to see the faint, messy blueprints of a beginning, but they are looking at a finished masterpiece that defies the laws of physics as we know them. It is as if we opened a book to the first page, only to find the ending already written. This discovery does more than just break our models of the early universe. It suggests that something about the way time, gravity, and matter interact is not what we believed. Now we are left to wonder if our story of the cosmos is missing its most important chapter. Tonight's journey is brought to you by Beyond the Stars, a full collection of overnight cosmic sleep journeys available at mycosmicdrift.com. Link in the description. For decades, the Hubble Space Telescope was our greatest window into the deep universe. It showed us galaxies stretching back billions of years, revealed the beauty of nebulae and dying stars, and gave humanity its first true glimpse of just how vast and ancient the cosmos really is. Hubble changed everything. Before it launched in 1990, astronomers debated whether the universe was 10 billion or 20 billion years old. Hubble helped settle the argument. It measured the distances to faraway galaxies with a precision that had never been achieved, and it helped pin the age of the universe at roughly 13.8 billion years. It captured images so deep that a single photograph contained thousands of galaxies, each one a swirling island of billions of stars. It gave us the Hubble Deep Field, a seemingly blank patch of sky that turned out to be teeming with galaxies stretching back to when the universe was less than 1 billion years old. That single image changed the way humanity understood its place in the cosmos. But Hubble had a limit. It could only see so far. Its mirrors and instruments were designed to capture visible light and a narrow band of ultraviolet and infrared. That meant the oldest, most distant galaxies were hidden from its view. Their light stretched so far by the expansion of the universe that it had shifted beyond what Hubble could detect. This is because of a phenomenon called redshift. As light travels through expanding space, its wavelength gets stretched. Blue light shifts toward red. Red light shifts into infrared. And infrared light shifts even further into wavelengths that Hubble was never built to see. The farthest objects in the cosmos glow not in visible light, but in deep infrared, a wavelength that is invisible to the human eye and largely invisible to Hubble as well. Think of it like this. If the universe is a symphony, Hubble could only hear the high notes. The deep rumbling bass of the oldest and most distant galaxies was completely silent to it. To hear those notes, to see the true beginning, we needed something new. Something that could listen in a completely different frequency. That something was the James Webb Space Telescope, and it was decades in the making. The idea for Webb first took shape in the mid-1990s, just a few years after Hubble launched. Scientists knew that the next great leap in space astronomy would require a telescope that saw primarily in infrared light. But building such an instrument was an enormous technical challenge. Infrared light is essentially heat radiation, which means the telescope itself would need to be kept fantastically cold to avoid drowning out the faint signals it was trying to detect. This requirement drove every aspect of the telescope's design, from its location in space to the massive sun shield that would protect it from the warmth of the sun, the earth, and the moon. The project took over 25 years and cost roughly $10 billion, making it one of the most expensive and ambitious space telescopes ever constructed. When it finally launched on Christmas morning of 2021, the entire scientific world held its breath. The telescope was folded up like a piece of origami inside the nose of an Ariane 5 rocket, and over the course of the next month, it slowly unfolded itself as it traveled to a point in space about 1.5 million kilometers from Earth. This location, known as the second Lagrange point, or L2, keeps the telescope in a stable orbit, where it can always face away from the Sun, the Earth, and the Moon. That matters because Webb sees in infrared, and infrared is essentially heat. To detect the faintest heat signatures from the oldest corners of the universe, the telescope itself has to be incredibly cold. A tennis court-sized sun shield made of 5 layers of a special material thinner than a human hair keeps it in permanent shadow, cooling its instruments to temperatures far below freezing, around -230 degrees Celsius. On one side of the sun shield, the temperature is hot enough to boil water. On the other side, it is colder than anything naturally found on the surface of any planet in our solar system. The mirror is another marvel. Webb's primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's mirror, which means it can collect roughly 6 times as much light. But a mirror that large cannot fit inside any existing rocket fairing in one piece. So engineers designed it as a collection of 18 hexagonal segments, each one made of beryllium and coated in a microscopically thin layer of gold. Gold was chosen because it is an excellent reflector of infrared light. Each segment had to be polished to a smoothness that is almost impossible to comprehend. If you scaled one of those mirror segments up to the size of the entire United States, the largest bump on its surface would be only a few inches tall. After launch, those 18 segments had to unfold and then align themselves to within 1/10,000th the width of a human hair. The fact that this worked at all is one of the greatest engineering achievements in history. There were hundreds of things that could have gone wrong during that journey. The sun shield alone had 344 points of failure. Each of the 5 layers had to deploy in the correct sequence, stretch to the correct tension, and separate from the others by precisely the right distance. If even one of those steps had not worked, the entire mission, 25 years of work and billions of dollars, would have been over before it began. Engineers and scientists around the world watched each step unfold with a mixture of hope and dread. Some described it as the most stressful month of their lives. But one by one, every mechanism clicked into place. The mirror segments aligned, the instruments powered on, the telescope cooled to its operating temperature. And for the first time in human history, we had an observatory powerful enough to look back to the very edge of time itself. Webb does not see galaxies the way Hubble did. It does not take pretty pictures of swirling spiral arms in visible light. Instead, it collects infrared light that has been traveling across the universe for billions of years, stretched and reddened by the expansion of space itself. This is a crucial concept to understand. So let us take a moment with it. When we look at a galaxy that is 13 billion light-years away, we are not seeing it as it is today. We are seeing it as it was 13 billion years ago, because that is how long the light has been traveling to reach us. The galaxy may have changed enormously in the intervening billions of years. It may have merged with other galaxies. It may have burned through all its gas and gone dark. It might not even exist anymore in any recognizable form. But the light we see left that galaxy 13 billion years ago and has been crossing the void of space ever since, carrying with it a frozen snapshot of a moment that is unimaginably ancient. In A very real sense, looking deeper into space means looking further back in time. Every telescope is a time machine, and Webb can look further back than anything we have ever built. The scientific community had predictions. They had models. They had decades of theory about what the early universe should look like. And those theories were not guesses. They were the product of thousands of scientists working for generations, refining equations, running simulations on the most powerful computers ever built, and testing their predictions against every piece of observational data available. The Standard Model of Cosmology is one of the most thoroughly tested frameworks in all of science. It describes the history of the universe from the Big Bang to the present with remarkable precision. According to that model, the universe began with the Big Bang, roughly 13.8 billion years ago. In the beginning, everything was compressed into a state of unimaginable density and temperature. Then, in a fraction of a second, space itself expanded at a rate faster than the speed of light, a process called inflation. After inflation ended, the universe was a seething ocean of particles and radiation too hot for atoms to exist, too chaotic for any structure to form. Over the next few 100,000 years, it slowly cooled, and as it cooled, the fundamental forces of nature began to sort things out. Gravity was the key player. It is the weakest of the four fundamental forces, far weaker than electromagnetism or the nuclear forces. But it has one crucial advantage. It is always attractive and it never turns off. Over time, even the slightest differences in density regions where there was just a tiny bit more matter than average became amplified. Gravity pulled matter toward these denser regions, making them denser still, which pulled in even more matter. It was a cosmic snowball effect operating on a scale that is almost impossible to comprehend. The first structures to form were clumps of dark matter called halos. Because dark matter does not interact with light, it could begin clumping together even before ordinary matter could. These halos provided the gravitational scaffolding, the skeleton on which everything visible would eventually be built. Ordinary matter, mostly hydrogen and helium gas, fell into the gravitational wells created by the dark matter halos. As the gas accumulated, it compressed and heated up. In the densest pockets, the pressure and temperature eventually became high enough for nuclear fusion to begin. The first stars ignited. Those first stars were expected to be enormous, maybe 1,000,000 times the mass of our sun, burning incredibly hot and bright, but dying young. Over hundreds of millions of years, these early stars would have forged heavier elements and scattered them into space when they exploded, seeding the gas clouds that would one day become the next generation of stars and eventually the first true galaxies. Generation after generation, the process repeated. Each cycle produced more heavy elements, more complex chemistry, more diverse stellar populations. Galaxies grew, slowly merging with their neighbors, gradually building up their mass over billions of years. It was supposed to be a slow process, a gradual building up from almost nothing. Think of it like building a city. You start with a few huts, then a village forms, then a town. Eventually, over centuries, the town grows into a city. Nobody expects to walk into a field and find a skyscraper. The building blocks have to come first. The infrastructure has to be laid. The materials have to be gathered. And that is exactly what the Standard Model predicted for the early universe. The first galaxies were expected to be small, faint and messy, little more than loose collections of young stars clumped together in the darkness. That is what every simulation predicted. That is what every textbook described. And that is what astronomers fully expected to see when Webb opened its eyes for the first time in the summer of 2022. But that is not what happened. The first deep field image from Webb was released in July of 2022, and it took the world's breath away. President Biden unveiled it at a special White House event, holding it up as a testament to what humanity can achieve when it works together across borders and generations. The image showed a cluster of galaxies called SMACs, Go723, as they appeared roughly 4.6 billion years ago. The cluster itself was impressive, a collection of galaxies bound together by gravity. But the real magic was behind the cluster, because SMACS 0723 is so massive, its gravity bends the light of even more distant galaxies, warping and magnifying them like a cosmic funhouse mirror. Some of the background galaxies appeared smeared into arcs and streaks, their light stretched and distorted by the immense gravitational field. And in that warped, magnified background, astronomers could see galaxies from the infant universe, galaxies that had never been seen before by any human instrument. The image contained thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Some of those galaxies had been glowing since the universe was less than 1 billion years old, and the image itself represented only 12.5 hours of Webb observing time. Hubble had taken weeks to create a comparably deep image of a different patch of sky. Webb had done it in half a day. Astronomers around the world stayed up through the night to download and analyze the data. Social media lit up with commentary from scientists who could barely contain their excitement. For many of them, this was the culmination of a career, a lifetime of work building toward this moment. And for a brief shining instant, the whole world was looking at the same image, the same ancient light, the same impossible depth of cosmic time. It was beautiful, but almost immediately something was wrong. Not wrong with the telescope. Webb was working perfectly. The problem was with what it was showing us. In the very first deep field images, astronomers saw galaxies, lots of them, far more than anyone had predicted, and they were not small, faint, or messy. They were massive, bright, structured. They looked like galaxies that should have taken billions of years to form, and yet they were sitting right there in the infant universe just a few 100 million years after the Big Bang. At first, many scientists assumed it had to be an error. The instruments were still being calibrated. Perhaps the data was off. Perhaps the filters were not tuned correctly. Perhaps what they were seeing was not really what it appeared to be. In the early days of any new telescope, mistakes happen. Light from a nearby object can be confused with light from a distant one. Brightness can be misinterpreted. Distances can be miscalculated. So the teams went back to the data. They rechecked the calibrations. They ran the numbers again. And while some of the initial estimates were revised slightly downward, the core finding held. There really were enormous galaxies in the earliest epoch of the universe, and there were far too many of them. It is worth understanding how astronomers figure out the mass of a galaxy that is billions of light years away, because the method itself reveals how careful and how uncertain this work can be. You cannot weigh a distant galaxy the way you weigh something on a scale. Instead, you look at the light it emits. Different types of stars produce different amounts of light at different wavelengths. A young, massive star burns blue and hot. An old, small star glows red and dim. By collecting images of a distant galaxy at multiple wavelengths of infrared light, astronomers can build a profile of its overall light output. Then they compare that profile to computer models of galaxies containing different mixtures of stars, different ages, different masses, different amounts of dust. The model that best matches the observed light gives you an estimate of how many stars the galaxy contains and therefore how massive it is. But it is an estimation. It depends on assumptions about how stars form, how they evolve, and how their light is modified by dust and distance. Change the assumptions and the mass estimate changes too. Now I shall. This is why the initial discovery of the impossible galaxies was greeted with such healthy skepticism. Scientists wanted to make sure the assumptions were right before accepting that the universe was fundamentally different from what they expected. One team, led by astronomer Ivo Labbé at Swinburne University of Technology in Australia, was among the first to sound the alarm. Working with the very first datasets released by Webb as part of the Cosmic Evolution Early Release Science program, they identified 6 candidate galaxies that dated back to a time when the universe was only about 3% of its current age. That is just 500 to 700 million years after the Big Bang. To put that in perspective, if the entire history of the universe were compressed into a single calendar year, with the Big Bang happening on January 1st, these galaxies would have existed by about January 12th. The Earth would not form until September. Dinosaurs would not appear until December 25th. All of recorded human history would fit into the last fraction of a second before midnight on December 31st. These galaxies were ancient beyond comprehension. And these were not small fledgling galaxies. They contained stellar masses up to 100 billion times that of our Sun. One of them appeared to have as many stars as our entire Milky Way galaxy does today, crammed into a universe that was barely old enough for the first stars to have formed at all. The Milky Way took over 13 billion years to accumulate its stars. This galaxy appeared to have done the same work in a few 100 million years. It was like finding a library full of books in a world where the printing press was invented yesterday. Joel Leger, an astronomer at Penn State, who helped model the light from these objects, described the finding in terms that shook the scientific community. He said the amount of mass they discovered meant that the known mass in stars at that period was up to 100 times greater than what anyone had previously thought. He added that the revelation that massive galaxy formation began extremely early in cosmic history upended what many scientists had considered settled science. The team gave these objects an informal name. They called them universe breakers because they seemed to break everything we thought we knew about how the cosmos evolved. Think about what that means for a moment. Our best models of the universe said that in the first few 100 million years, gravity should have only managed to pull together small clumps of matter. The dark matter halos that serve as the scaffolding for galaxies were supposed to be modest in size. There simply was not enough time for gravity to gather 100 billion stars worth of material into a single structure. It would be like planting a seed in the desert yesterday and finding a fully grown oak tree this morning. The math does not work. The physics does not allow it. And yet, there it was. Let that analogy sink in for a moment. Imagine you know exactly how fast a tree grows. You know how much water it needs, how much sunlight, how long it takes for the roots to spread and the trunk to thicken and the branches to reach toward the sky. You have studied trees your entire career, and then one morning you walk outside and there is a 300-year-old oak standing in a field where bare dirt existed the day before. You check your instruments, you check your calendar, you check the soil. Everything confirms that this tree appeared overnight. Your first reaction is disbelief. Your second reaction is to check for an error. And your third reaction, once you have ruled out every possible mistake, is a strange mixture of excitement and terror. Because if the tree is real, then everything you thought you knew about how trees grow is wrong. That is what the impossible galaxies did to cosmology. And the scale of the problem only grew as more data arrived. These initial 6 galaxies were just the beginning, the tip of an iceberg that nobody had anticipated. As Webb continued to observe more and more unexpectedly, massive early galaxies appeared in the data. Some were found in dedicated deep field surveys. Others turned up in the backgrounds of images taken for entirely different purposes. It was as if the early universe was saturated with objects that defied explanation. In a study published in the summer of 2025, researchers at the University of Missouri used Webb's infrared cameras to identify 300 objects in the early universe that were brighter than they should be. 300 candidate galaxies that did not fit the models. Each one a tiny spark of light from billions of years ago, each one whispering the same message. We are here. We are bigger than you expected. And we need an explanation. The researchers used an established technique called the dropout method to identify their candidates. The idea behind this technique is clever. As light from a very distant galaxy travels through the expanding universe, its shortest wavelengths get stretched beyond detection. The galaxy literally drops out of visibility at certain wavelengths. By looking for objects that are visible in some of Webb's infrared filters, but invisible in others, astronomers can identify galaxies at extreme distances. The pattern of which filters show the galaxy, and which do not, tells you approximately how far away it is. It is like identifying a person's nationality by which languages they speak and which they do not. The process of figuring out what these objects really are is painstaking. You do not get a nice clear photograph of a galaxy that is 13 billion light-years away. Most of these objects appear as tiny fuzzy blobs, barely distinguishable from the background noise. Scientists have to act as cosmic detectives, piecing together clues from the limited light they can collect. They take images at different wavelengths of infrared light and compare them to computer models of galaxies with different ages, sizes, and star populations. It is an estimation, not a direct measurement, and that leaves room for uncertainty. Some of the initial mass estimates turned out to be too high. One of the original 6 universe breakers, for example, was later found to be closer than originally thought, which meant it was not actually in the very early universe at all. Calibration refinements brought other estimates down as well, but the core findings survived every check. There really were galaxies in the first 700 million years of cosmic history that were far more massive than any model predicted. The question was no longer whether these objects existed. The question was how. The impossible galaxies were not just a curiosity. They were a direct challenge to the lambda CDM model, the standard framework that describes how the universe has expanded and evolved since the Big Bang. Lambda stands for dark energy, the mysterious force that is accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible substance that makes up roughly 85% of all mass in the cosmos. Together, these two components, along with ordinary matter, form the backbone of our understanding of cosmic history. And the lambda CDM model has been remarkably successful. It accurately predicts the cosmic microwave background radiation, the large-scale structure of the universe, and the way galaxies are distributed across space. It tells us the age of the universe to within a fraction of a percent. It describes how the first atoms formed, how the cosmic web took shape, and how galaxies grew over billions of years. It is one of the most thoroughly tested and precisely calibrated models in all of science. But it does not predict galaxies this massive, this early. So what could explain them? Scientists have been exploring several possibilities, and each one reveals something fascinating about how the early universe might have worked differently than we assumed. One explanation that gained traction in 2023 and 2024 is called bursty star formation. The idea is that some galaxies in the early universe did not form stars at a steady, gradual pace. Instead, they went through intense, short-lived episodes of furious star creation, like a fireworks display compared to a steady candle flame. During these bursts, a galaxy could briefly appear much brighter than it would during quieter periods. If Webb happened to catch a galaxy during one of these bursts, it would look more massive than it actually was, because the brightness from the burst would inflate the estimated stellar mass. Think of it like a firefly. If you only see the flash, you might think the firefly is much larger and brighter than it really is. But if you could watch it over a longer period, you would see that most of the time it is dim and small, with occasional flashes that make it look impressive. This explanation accounted for some of the impossible galaxies, but not all of them. The bursts would have to be extraordinarily intense and extraordinarily common to explain the sheer number of massive objects Webb was seeing. And some of the galaxies showed evidence of mature stellar populations' old stars that could not have formed in a recent burst. Something more was needed. Another possibility involves the role of supermassive black holes. We know that when a black hole at the center of a galaxy is actively feeding it, can produce an enormous amount of light. This light comes not from the black hole itself, but from the superheated gas spiraling into it, a structure called an accretion disk. In some cases, the accretion disk can outshine all the stars in the galaxy combined. If some of the impossible galaxies had active supermassive black holes at their centers, the extra light from those black holes could make the galaxies appear much more massive than they actually were. In August of 2024, scientists from the Cosmic Evolution Early Release Science team confirmed that active black holes were indeed contributing extra brightness to many of the early galaxies Webb had observed. When they accounted for this contribution, some of the mass estimates came down significantly, but this raised a new puzzle. If these early galaxies had active supermassive black holes, where did those black holes come from? A supermassive black hole is not something that forms overnight. In our current understanding, they grow gradually over billions of years, feeding on gas and merging with other black holes. Finding them in the infant universe just a few 100 million years after the Big Bang is itself a challenge to explain. It is like solving one mystery only to find an even deeper mystery hiding behind it. If even one of those original 6 universe breakers turned out to be real, it would be a serious problem. And so began one of the most intense periods of investigation in modern astronomy. Teams around the world scrambled to figure out what was going on. Were these objects truly as massive as they appeared? Were they really as far away as the data suggested? Or was something else entirely going on, something no one had considered before? The answer, as it turned out, was more complicated and more fascinating than anyone expected. Some of the impossible galaxies were in fact not quite what they seemed. A portion of the initial shock was due to calibration issues with the new instruments. When those calibrations were refined, a few of the mass estimates came down, but others held firm. And then a new mystery appeared, one that would take the story in a direction no one had predicted. Scattered throughout the earliest images from Webb astronomers began to notice something strange. Tiny points of reddish light, barely visible even to the most powerful telescope ever built. They were compact, incredibly bright for their size, and they appeared in almost every single deep field image the telescope captured. At first, nobody knew what they were. They were too small to be typical galaxies, too bright to be single stars, and too red to match anything in the existing catalogues of astronomical objects. Scientists started calling them the little red dots, a casual nickname that stuck even as the objects themselves became one of the biggest mysteries in modern astrophysics. It was as if the baby universe had caught a case of measles. Everywhere Webb looked, there they were. Little red specks dotting the darkness of the ancient cosmos. If you find yourself coming back to videos like this one to fall asleep, there's a reason. Your mind needs somewhere to go. Not music, not silence. Something steady to follow. Beyond the Stars is a full collection of overnight narrated space journeys. 5 tracks, 6 to 8 hours each. No ads, no endings, no interruptions. $39, once, any device. Link is in the description. We'll be back in a moment, like freckles on a face. And the more astronomers searched, the more they found. The little red dots were everywhere. By 2025, astronomers had identified 341 of them, and the number kept growing with every new survey. They existed primarily in the first billion years of the universe, between about 600 million and 1.6 billion years after the Big Bang. And they were strange in ways that went beyond just their appearance. To understand why, you need to know a little about how astronomers study distant objects. When a telescope captures light from something billions of light years away, that light carries information encoded in its wavelengths. By breaking that light into its component colors, a process called spectroscopy, scientists can learn an enormous amount about the source. They can determine its temperature, its chemical composition, how fast it is moving, and whether it is powered by stars, by a black hole, or by something else entirely. The spectrum of an object is like its fingerprint. No two types of objects have exactly the same one. The spectra of the little red dots did not match any known type of object. They had a peculiar V-shaped pattern, blue in the ultraviolet and deeply red in the optical. Some showed broad emission lines, a telltale sign of gas moving at extreme speeds near a supermassive black hole. Others showed features that looked more like the atmospheres of cold, dim stars. It was as if each little red dot contained a contradiction. They were simultaneously too hot and too cold, too massive and too compact, too bright and too strange. Every time scientists thought they had figured out what these objects were, another piece of data came along and complicated the picture. Early theories tried to explain them as comet galaxies packed with an impossibly dense number of stars. But the density required would have been extraordinary. The night sky of such a galaxy would have been dazzlingly bright, with stars packed so closely together that the spaces between them would barely exist. If you stood on a planet inside one of these objects, looking up would be like staring into a wall of light. There would be no darkness between the stars, just an unbroken glow stretching from horizon to horizon. It is a beautiful image, but the physics required to create it seemed impossible. Other researchers proposed that the little red dots were actually active galactic nuclei, the brilliant cores of galaxies, powered by supermassive black holes gorging on surrounding matter. When a black hole feeds the material spiraling into it, forms a disk of superheated gas that can outshine the entire galaxy around it. This explanation fits some of the data, but it had problems too. Active galactic nuclei typically emit X-rays, and when astronomers pointed X-ray telescopes at the locations of known little red dots, they found nothing. No X-ray emission at all. Their spectra also did not match the pattern seen in known dust-reddened active galactic nuclei, the dusty, obscured black holes that astronomers had studied for decades. Then there was the dust theory. Some researchers thought that perhaps the little red dots were normal galaxies, or black holes hidden behind thick clouds of cosmic dust. Dust absorbs shorter wavelengths of light, including ultraviolet and X-rays, and re-emits that energy at longer wavelengths in the infrared and millimeter range. If dust was responsible for the red color, then looking at the little red dots at even longer wavelengths should reveal the re-emitted energy. Astronomers tested this using Webb's mid-infrared instrument and the Atacama Large Millimeter Array, one of the most powerful ground-based telescope arrays in the world, located high in the Chilean desert. They pointed both instruments at 60 known little red dots and looked for the telltale glow of warm dust. They found nothing. No millimeter emission, no mid-infrared excess. The little red dots were not dusty. Whatever was making them red, it was not a shroud of cosmic dust hiding a normal galaxy underneath. The color was intrinsic to the objects themselves. As one researcher put it, what we are seeing is really the light that is coming from this thing, whatever it is. That result was decisive. It eliminated one of the most popular explanations and left scientists with a genuine mystery. An object that is too bright to be a normal galaxy, too compact to be resolved into a recognizable shape too red, to be a typical active galactic nucleus, and not dusty enough for dust to explain any of it. Something entirely new was needed. Something was not adding up. And then came the cliff. To understand this next part of the story, you need to know about a program called RUBIES. It stands for Red Unknown's Bright Infrared Extra Galactic Survey, and it was designed specifically to solve the mystery of the little red dots. The program was formulated by Anna de Graaf at the Max Planck Institute for Astronomy in Heidelberg, Germany, along with an international team of colleagues. They applied for observing time on Webb, competing against hundreds of other proposals from astronomers around the world. Webb is the most sought-after telescope in history, and the competition for its time is fierce. Every hour of observation has to be justified, defended, and approved by a review committee. The RUBIES proposal was successful. Between January and December of 2024, the astronomers used nearly 60 hours of Webb time to obtain spectra from a total of 4,500 distant galaxies. This was one of the largest spectroscopic datasets ever collected with the telescope. Spectroscopy is far more demanding than imaging. Taking a picture of a distant galaxy might require minutes or hours. Taking a spectrum which breaks the light into its component, wavelengths, and measures the intensity at each one can require many hours for the faintest objects. And the little red dots are among the faintest objects Webb can see. They are at the very limits of the telescope's capability, which is saying something for the most powerful observatory ever built. Within that enormous dataset, the team found 35 little red dots. Most of them had already been identified in publicly available images. But the new ones, the ones that emerged from the spectroscopy for the first time, turned out to be the most extreme and fascinating of all. In July of 2024, the most remarkable spectrum appeared. It belonged to a little red dot that the team would nickname the Cliff because of a dramatic feature called a Balmer break. A Balmer break is a sharp jump in brightness at a specific wavelength that is associated with the hydrogen in stellar atmospheres. It occurs because hydrogen atoms absorb light at certain wavelengths very efficiently, creating a step in the spectrum where the brightness suddenly drops. Balmer breaks are common in many types of astronomical objects, but the Cliff's Balmer break was unlike anything ever recorded. It was so steep, so sharp, so dramatic, that no existing model of galaxies or active galactic nuclei could reproduce it. The light from this object had traveled nearly 12 billion years to reach Earth, meaning it existed when the universe was only about 2 billion years old. Anna de Graaf said that the extreme properties of the Cliff forced them to go back to the drawing board and come up with entirely new models. And what they came up with was extraordinary. They proposed that the Cliff and potentially many other little red dots might represent an entirely new class of cosmic object, not a galaxy, not a typical black hole, something in between, something that had never been seen before. They called it a black hole star. The idea is both simple and staggering. Imagine a supermassive black hole millions of times the mass of our Sun, sitting at the center of a vast cloud of hydrogen gas. The black hole is feeding ravenously, pulling in matter at an extraordinary rate. As the gas falls inward, it heats up, releasing enormous amounts of energy. But instead of that energy escaping freely as it does in a typical active galactic nucleus, it is trapped. The surrounding gas is so thick, so dense that it forms a cocoon around the black hole, absorbing the radiation and re-emitting it at longer, redder wavelengths. The result is an object that looks from the outside like a colossal star. It has the spectral signature of a stellar atmosphere. It glows red. It is compact, but at its heart, it is not powered by nuclear fusion like a normal star. It is powered by a black hole devouring everything around it. Picture it this way. If you could somehow shrink yourself down and fly toward a black hole star, here is what you might see. From a distance, it would look like an enormous red sphere larger than our entire solar system, glowing with a warm, ruddy light. As you got closer, you would feel the heat intensify. The surface, if you can call it that, would be a roiling, turbulent layer of hydrogen gas churning and billowing like the surface of a sun, but far more violent. And if you could somehow peer through that thick outer shell, you would see the source of all that energy, a black hole at the very center, pulling in gas from every direction, heating it to millions of degrees as it spirals inward on its final journey to the point of no return. The black hole would be invisible, of course. You cannot see a black hole directly. But you would see its effect on everything around it, the gas, glowing white hot as it falls in the jets of energy, screaming outward at nearly the speed of light, all of it hidden from the outside universe by that thick, opaque blanket of hydrogen. It is a cosmic disguise, a black hole wearing the mask of a star. Rohan Naidu, an astrophysicist at the Massachusetts Institute of Technology, who has been at the forefront of this research, said that he believes this is by far the most exciting discovery to come out of Webb. He described the little red dots as appearing in every single image the telescope takes, and he added that it is very rare in astronomy to come across an entirely new class of object. He is now dedicating his full research effort to understanding them. If you start thinking about them as essentially this enormous star that has a black hole at its center, he said things start falling into place. The sheer ubiquity of the little red dots is one of the most striking aspects of this mystery. They are not rare. They are not confined to one patch of sky or one particular survey. They show up everywhere. Webb looks in every deep field, in every spectroscopic campaign, in the backgrounds of images taken for completely unrelated purposes. As of 2025, 341 have been formally catalogued, but that number is growing with every new dataset. Some estimates suggest there could be thousands or tens of thousands more waiting to be found in future surveys. If even a significant fraction of these objects turn out to be black hole stars, it would mean that this previously unknown phase of cosmic evolution was not an anomaly. It was the norm. The early universe may have been teeming with objects that we had no idea existed until Webb showed them to us. And here is something that makes the discovery even more remarkable. The little red dots seem to disappear at later, cosmic times. They exist in abundance in the first billion years of the universe, but they become increasingly rare as the cosmos ages. By the time the universe is a few billion years old, they are essentially gone. Whatever these objects are, they represent a transient phase, a brief but intense period in the evolution of the universe that left its mark and then vanished. Understanding what they transformed into, whether they became the cause of modern galaxies, collapsed into the supermassive black holes we see today, or evolved into something else entirely, is one of the key questions for future research. This idea, if confirmed, would reshape our understanding of how galaxies form. Before Webb, the prevailing view was that galaxies formed first slowly building up over billions of years, and that supermassive black holes grew within them over time. The black hole was always seen as a consequence of galaxy evolution, a parasite that grew inside the host. But the black hole star model flips that narrative entirely. It suggests that black holes may have come first, growing rapidly in these dense gas cocoons, and that galaxies formed around them later. The galaxy would not create the black hole. The black hole would create the galaxy. It is a complete reversal of cause and effect, and if it turns out to be true, it would be one of the most significant shifts in our understanding of cosmic evolution in decades. The implications ripple outward in every direction. If black holes came first, then the entire process of galaxy formation needs to be rethought. The models that describe how gas flows into dark matter halos, how it cools and fragments into stars, how those stars pump energy back into their surroundings, all of these would need to be revised to account for a massive black hole sitting at the center of the process from the very beginning. It would mean that the seeds of the largest structures in the universe were not stars at all, but black holes. Darkness before light, consumption before creation. And there is another implication that connects to one of the most important transitions in the history of the universe. It is called the Epoch of Reionization, and it is the moment when the cosmos went from dark to light on a grand scale. To understand this event, imagine the universe as a vast, dark room filled with fog. The fog is made of neutral hydrogen gas, trillions upon trillions of atoms drifting in the darkness. After the cosmic microwave background was released about 380,000 years after the Big Bang, this was exactly what the universe looked like. A cold, dark, foggy void. No stars, no light, just gas and gravity and silence. Then the first sources of light appeared. Stars ignited. Black holes began to feed. Energy poured into the surrounding gas. But that light could not travel far. The neutral hydrogen absorbed ultraviolet radiation, hungrily soaking it up like a sponge. For a photon of ultraviolet light, the universe was a prison. It could only travel a short distance before being absorbed by a hydrogen atom. The universe was lit from within, but still opaque like a light bulb inside a cloud. But here is the key. When an ultraviolet photon strikes a neutral hydrogen atom with enough energy, it knocks the electron free, ionizing the atom. Once ionized, that hydrogen atom can no longer absorb ultraviolet light. It becomes transparent. So as the first stars and black holes poured energy into their surroundings, they carved out bubbles of ionized transparent gas in the otherwise opaque fog. Each source of light created its own little clearing, like a candle melting a hole in a wall of ice. Over hundreds of millions of years, those bubbles grew and merged. New sources of light appeared, creating new bubbles that expanded into the remaining fog. The process was uneven and messy. Some regions of the universe became transparent long before others. The cosmic fog did not lift all at once. It was eaten away piece by piece, bubble by bubble, until eventually, by about 1 billion years after the Big Bang, the Reionization was essentially complete, and light could travel freely across the cosmos. The universe had gone from opaque to transparent, from dark to light, and it would never go back. But here is the problem that has troubled astronomers for years. When they add up all the known sources of ultraviolet radiation from that era, all the stars in all the galaxies that Webb and Hubble have detected, there does not seem to be enough energy to do the job. The galaxies we can see are not producing enough ultraviolet light to reionize the entire universe on the timeline we observe. Something is missing from the equation, some source of energy that we have not accounted for. This is where the little red dots become important again. If they turn out to be black hole stars, their intense radiation could have contributed significantly to this process. A supermassive black hole wrapped in a cocoon of hot glowing gas would be a powerful source of ionizing energy, pouring out photons in every direction. And because little red dots appear to be common in the early universe, appearing in essentially every deep field image Webb takes, their collective contribution to reionization could be substantial. They might be part of the missing piece that explains how the universe lit up. The black hole stars would be a missing link, a never-before-seen phase in the life cycle of the most massive structures in the universe. They would connect the dark ages to the dawn, the silence to the first sound. And there is yet another puzzle that black hole stars might help solve. Astronomers have long wondered where supermassive black holes come from. These objects, which sit at the centers of nearly every large galaxy, are millions or billions of times the mass of our Sun. They are too massive to have formed from the collapse of a single star, even the largest star imaginable. When a massive star dies, its core collapses into a black hole, but that black hole typically has a mass of only a few dozen times that of our Sun. To get from a few dozen solar masses to millions or billions of solar masses, the black hole would need to feed continuously for billions of years, consuming gas and merging with other black holes. But that takes time, a lot of time. And Webb has been finding evidence of high-mass black holes existing in the very early universe, just a few 100 million years after the Big Bang, when there simply has not been enough time for that gradual process to work. This is one of the most important open questions in astrophysics. How do you build a billion solar mass black hole in less than a billion years? There are really only a few options. One is that the black holes started from very large seeds. Instead of forming from the collapse of a single star, they might have formed from the direct collapse of a massive cloud of gas, creating a seed black hole that was already thousands or tens of thousands of times the mass of our Sun. That gives it a head start. Another option is that the black holes grew faster than we thought was possible, exceeding the theoretical limit called the Eddington rate. The Eddington rate is the maximum speed at which a black hole can swallow matter, based on the balance between the inward pull of gravity and the outward push of radiation pressure. If a black hole tries to eat too fast, the energy it releases pushes the food away. But some models suggest that under certain conditions, black holes can exceed this limit, gorging themselves in a frenzy of rapid growth. If black hole stars are real, they offer a third option that is perhaps the most elegant. A black hole star is essentially a natural incubator for a supermassive black hole. The dense gas envelope traps the radiation, preventing it from pushing the inflowing gas away. The black hole can feed at rates far exceeding the Eddington limit, hidden inside its cocoon, growing rapidly and unseen. When the gas envelope is finally exhausted, what emerges is a ready-made supermassive black hole born not through billions of years of gradual accretion, but through a relatively brief, intense phase of turbocharged growth. Joel Lager, who was part of the team that first identified the universe breakers, put it this way: nobody has ever really known why or where the gigantic black holes at the center of galaxies come from. These black hole stars might be the first phase of formation for the black holes that we see in galaxies today, supermassive black holes in their little infancy stage. But the mystery does not end there, because even as the black hole star theory was gaining traction, new discoveries kept pushing the story further. In early 2025, astronomers announced the discovery of the most distant little red dot ever found, designated Kuiper's LRD-Z9. It has a redshift of 9.3, which means its light has been traveling for over 13 billion years. We are seeing this object as it existed just 500 million years after the Big Bang. At its center sits a supermassive black hole, estimated at roughly 38 million times the mass of our Sun, shrouded in a dense shell of dusty gas. What makes this object especially important is what it tells us about how quickly black holes can grow. To reach 38 million solar masses in just 500 million years, the black hole would have needed to start as an unusually large seed and grow at or above the theoretical maximum rate, or it would have needed to start smaller and grow at rates that exceed the theoretical limit. Both scenarios are extraordinary. Both push the boundaries of our physics, and both suggest that the early universe had mechanisms for rapid black hole growth that we do not fully understand. Here is what that means in plain language. The most distant little red dot is telling us that supermassive black holes existed earlier, grew faster, and were more common than any theory predicted. And every new little red dot that Webb discovers deepens that message. Because even as scientists were grappling with the impossible galaxies and the little red dots, Webb was revealing something else about the early universe, something that connects to a much deeper question about the invisible substance that holds everything together. Dark matter. We cannot see it. We cannot touch it. It does not emit light, reflect light, absorb light, or even block light. It passes through ordinary matter like a ghost. And yet, it makes up roughly 85% of all the mass in the universe. We know it exists because of its gravity. Galaxies spin too fast to hold themselves together with visible matter alone. If you add up all the stars, all the gas, all the dust in a galaxy like the Milky Way, there is simply not enough mass to explain why the outer stars orbit at the speeds they do. Without something extra holding it together, our galaxy should have flown apart billions of years ago. The same is true for galaxy clusters. They are too massive to be explained by the stars and gas we can see. And the entire large-scale structure of the universe, the way galaxies are arranged in vast filaments and walls separated by enormous voids, only makes sense if there is an invisible scaffolding holding it all in place. That scaffolding is dark matter. For decades, dark matter has been one of the great frustrations of physics. We know it is there. We can measure its effects with extraordinary precision, but we have no idea what it actually is. It is not made of atoms or any form of ordinary matter. It does not interact with the electromagnetic force, which is why it neither emits nor absorbs light. Trillions of dark matter particles could be streaming through your body right now, and you would never know it. Hundreds of experiments around the world have tried to detect dark matter particles directly using underground laboratories, particle colliders, and sensitive detectors buried deep in mountains. So far, none of them have succeeded. Whatever dark matter is, it remains stubbornly invisible. But Webb has given us a new way to study it. In January of 2026, a team of scientists using Webb produced the most detailed map of dark matter ever created. Using data from the Cosmos Webb survey, they analyzed nearly 800,000 galaxies in a patch of sky, about 2.5 times the size of the full moon. They were not looking at the galaxies themselves. They were looking at how the galaxies appeared slightly distorted, their shapes bent and stretched, by the gravitational pull of invisible matter between them and the telescope. This technique, called weak gravitational lensing, is like reading the presence of a heavy object on a trampoline by watching how marbles roll around it. You cannot see the object directly, but you can see its effect on everything nearby. The concept is beautifully simple, even if the execution is fantastically difficult. Light always travels in straight lines through empty space. But when light passes near a massive object, gravity bends its path, curving it slightly toward the source of the gravity. This effect, predicted by Albert Einstein more than a century ago, has been confirmed countless times. For the dark matter map, scientists looked at how the shapes of distant galaxies were distorted by the gravitational pull of dark matter sitting between those galaxies and Webb. Each individual distortion is tiny, far too small to see with the naked eye, changing a galaxy's shape by about 1%. But by measuring the shapes of hundreds of thousands of galaxies and comparing them to what those shapes should look like, without any distortion, scientists can build a statistical picture of where the dark matter is concentrated. Webb is uniquely suited for this kind of work because its sharp optics and infrared sensitivity allow it to resolve far more galaxies than any previous telescope. Hubble could measure about 71 galaxy shapes per square arc-minute of sky. Webb can measure 129. That almost doubles the amount of information available for mapping the invisible mass of the universe. What the map revealed was stunning. Dark matter and ordinary matter are not just loosely connected. They are intertwined at every scale. Wherever there is a massive cluster of galaxies, there is an equally massive concentration of dark matter. Wherever a thin filament of galaxies stretches between two clusters, a corresponding strand of dark matter runs alongside it. The map revealed a network of filamentary bridges like the strands of a colossal spider web, stretching between galaxy clusters across millions of light years. These filaments had been predicted by computer simulations for decades, but seeing them with this level of clarity in real observational data was something new. If you could somehow zoom out and see the entire observable universe at once, this is what it would look like. Not a uniform scattering of galaxies, but a vast three-dimensional web. The densest nodes of the web are galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity and swimming in a sea of hot gas. Connecting those nodes are the filaments, long, thin structures stretching hundreds of millions of light years, along which smaller galaxies are strung like beads on a thread. And between the filaments are the cosmic voids, enormous empty spaces where almost no galaxies exist, regions of near-perfect nothingness that can span hundreds of millions of light years across. The universe is not full. It is mostly empty, and the structures that exist within that emptiness are organized in a pattern that looks hauntingly like the neurons in a human brain, or the mycelium network of a fungus spreading through the soil. It is a cosmic web, and dark matter is the architect that built it. What makes the Webb map special is its resolution. Previous dark matter maps, including one made of the same patch of sky using Hubble data back in 2007, could see the larger structures, the massive clusters, the thickest filaments, but the details were blurry. Smaller galaxy groups were invisible. Finer filaments were lost in the noise. Webb, with its sharper optics and ability to measure the shapes of nearly twice as many galaxies per unit of sky, revealed structures that had never been seen before. It was like going from a blurry photograph to a high-definition image. The same landscape, but suddenly you can see the individual trees. Richard Massey, an astrophysicist at Durham University in the United Kingdom, who helped create the map, described it in striking terms. He said that wherever they see a big cluster of thousands of galaxies, they also see an equally massive amount of dark matter in the same place. And when they see a thin string of regular matter connecting two of those clusters, they see a string of dark matter as well. He added that it is not just that they have the same shapes. The map shows that dark matter and regular matter have always been in the same place. They grew up together. This finding supports the standard picture of cosmic evolution in one important way. Dark matter is supposed to be the architect. It clumped together, first pulling in ordinary matter through gravity, creating the dense regions where stars and galaxies eventually formed. The Webb map confirms this general framework, but it also raises new questions because the structures it reveals are finer and more complex than previous maps could show. Some features that were invisible in the earlier Hubble-based maps are now clearly visible, including smaller galaxy groups and delicate filamentary bridges that connect larger structures across millions of light years. And dark matter is connected to the impossible galaxies problem in a very direct way. Under the standard model, dark matter collapsed into halos within the first few 100 million years after the Big Bang. Those halos provided the gravitational wells into which ordinary matter fell, eventually forming stars and galaxies. But the standard model also predicts how many halos should have existed at any given time and how massive they should have been. The impossible galaxies that Webb found require far more dark matter halos and far larger ones than the model predicts for that era. Either the model is wrong about how dark matter behaves in the early universe, or something else is going on that we have not yet figured out. Here is something that few people realize about dark matter, something that makes the problem even more interesting. We know that dark matter interacts with gravity. That is how we detect it. But we do not know whether dark matter interacts with itself. In most models, dark matter particles pass through each other like ghosts, never colliding, never clumping together through any force other than gravity. But what if that assumption is wrong? What if dark matter particles can interact with each other through some unknown force, something weaker than electromagnetism, but stronger than gravity? If they can, it would change the way dark matter halos form. They might form faster or differently or at different sizes. And that could change the predictions for how many massive galaxies should exist in the early universe. This is one of the reasons the Cosmos Webb dark matter map is so important. By comparing the detailed structure of the dark matter distribution to the predictions of different dark matter models, scientists can begin to test these ideas. If the real dark matter distribution differs from the cold dark matter prediction in specific predictable ways, it could point toward a new understanding of what dark matter actually is. The map is not just a picture. It is a diagnostic tool, a way to probe the fundamental nature of one of the most mysterious substances in the universe. One possibility that has captured the imagination of physicists is the idea of dark stars. Not to be confused with black hole stars, dark stars are a different theoretical concept entirely. First proposed in 2008 by physicist Catherine Fries, the idea is that in the very early universe before the first normal stars ignited, there may have been objects powered not by nuclear fusion, but by the annihilation of dark matter. The concept works like this. In regions where dark matter was particularly dense, particles of dark matter could have collided with their antiparticles, releasing energy. This is not science fiction. It is a direct prediction of many particle physics models. If dark matter is made of particles that have antiparticles, and if those particles are concentrated enough, they will occasionally find each other and annihilate, converting their mass into pure energy according to Einstein's famous equation. In a normal star, the energy that holds it up against gravity comes from nuclear fusion in the core hydrogen atoms smashing together to form helium-releasing energy in the process. But in a dark star, the energy comes from dark matter annihilation. This might seem like a small difference, but its consequences are enormous. Dark matter annihilation produces energy at a much slower rate than nuclear fusion, which means dark stars would be cooler than normal stars. But they would also be far more massive because the slower energy production means gravity can pull together much more material before the outward pressure of energy balances the inward pull of gravity. A dark star could grow to be truly gigantic, possibly 1,000,000 times the mass of our Sun, with a luminosity billions of times greater. It would be an object unlike anything in the modern universe. These supermassive dark stars could have lived for millions of years before eventually exhausting the dark matter fuel in their vicinity. Without that fuel, the energy propping them up against gravity would disappear, and the entire massive structure would collapse. What would it collapse into? A supermassive black hole. And that is the key insight. Dark stars could provide a direct pathway from the primordial universe to the supermassive black holes that we see at the centers of galaxies today. No need for billions of years of gradual growth. No need for a galaxy to form first. The dark star forms, feeds on dark matter, grows enormous, and then collapses in a cosmic instant, creating a ready-made supermassive black hole. In October of 2025, a team led by Cosmin Ely of Colgate University published a study identifying 4 objects in Webb data, whose appearance and spectral signatures match what scientists expect from supermassive dark stars. The objects are extremely distant and extremely bright, and their properties do not fit neatly into any existing category of known astronomical objects. If confirmed, these objects could help solve 2 of the biggest puzzles in early universe astronomy at once. They could explain where the impossibly bright galaxies came from, because a supermassive dark star would be bright enough to be mistaken for an entire galaxy. And they could explain the origin of the supermassive black holes that power the most distant quasars ever observed, because those black holes would be the direct descendants of collapsed dark stars. It is a beautiful theory. Elegant, testable, and deeply connected to the mysteries Webb is uncovering. But it is also far from proven. The 4 candidate objects need much more study. Their spectra need to be confirmed. Alternative explanations need to be ruled out. Science is a slow, careful process, and extraordinary claims require extraordinary evidence. But the fact that dark stars have gone from a theoretical curiosity to a testable hypothesis thanks to Webb is itself a remarkable development. But we are getting ahead of ourselves, because there is yet another piece of this cosmic puzzle, one that connects the impossible galaxies to the very first light that ever shone in, the universe. Long before any galaxy existed, long before any black hole formed, long before the cosmic web of dark matter took shape, the universe was dark. After the Big Bang, the cosmos was a hot, dense fog of particles. Protons, neutrons, electrons, and photons were all tangled together in a searing plasma so hot that light could not travel more than a short distance before being absorbed. For the first few 100,000 years, the universe was opaque. If you could have been there, you would not have seen anything at all. Not because there was nothing to see, but because light itself was trapped, bouncing endlessly between particles like a ball in a room with no doors. Then about 380,000 years after the Big Bang, something remarkable happened. The universe cooled enough for the first atoms to form. Protons captured electrons and became hydrogen atoms. Helium nuclei grabbed their own electrons, and suddenly the fog cleared. Light was released in a great flash that traveled outward in every direction, filling the entire cosmos with radiation. We still see that flash today. It is the cosmic microwave background radiation, the faint afterglow of creation, that fills every corner of the sky. It has been stretched by the expansion of the universe from its original fierce glow into a whisper of microwave radiation just a few degrees above absolute zero. But it is there everywhere, a snapshot of the universe as it was 380,000 years old. It is the oldest light we can see. But after that flash, the universe went dark again. There were no stars, no galaxies, no sources of light at all. Just vast clouds of hydrogen and helium drifting in the blackness, slowly falling under the pull of gravity into the densest pockets of dark matter. This era is known as the Cosmic Dark Ages, and it lasted for roughly 100 to 200 million years. It is the most mysterious period in the history of the universe because we have almost no observational data from it. It exists in a gap between the cosmic microwave background and the oldest stars and galaxies we have ever detected. And then somewhere in that darkness something ignited. Deep within the densest concentrations of dark matter, gravity pulled enough gas together to create the conditions for the unthinkable. Clouds of hydrogen and helium, some of them thousands of light years across, began to collapse under their own weight. As the gas fell inward, it compressed and heated. The center of each collapsing cloud grew denser and hotter minute by minute, century by century, until the pressure became so intense and the temperature so extreme that hydrogen atoms began to fuse. 4 hydrogen nuclei slammed together and became one helium nucleus, releasing a tiny burst of energy. Then another fusion, and another, and another. The first nuclear fires were lit. The first photons of starlight burst outward through the darkness, pushing against the infalling gas, finding a balance between the crush of gravity and the fury of fusion. A star was born. This moment, this transition from absolute darkness to the first glimmer of light is called the cosmic dawn. And it was not a single event, but a process unfolding across millions of years and billions of light years. If you could have been there to witness it, what would you have seen? In most of the universe, nothing, just darkness, cold gas drifting silently through the void. But if you happened to be near one of the densest knots of dark matter, you might have seen something extraordinary. A faint glow emerging from the heart of a collapsing gas cloud. A pinprick of blue-white light where none had existed before. And then another nearby, and another. Each one a new star, a new source of energy, a new beacon in the blackness. The cosmic dark ages were ending, and the universe would never be dark again. These were the population 3 stars, a name that comes from an old astronomical naming convention, where stars are classified by their chemical composition. Population I stars like our Sun are rich in heavy elements. Population 2 stars found in the oldest regions of our galaxy contain fewer heavy elements. Population 3 stars are the theoretical first generation composed almost entirely of hydrogen and helium, with only trace amounts of lithium, the lightest elements left over from the Big Bang itself. They contained none of the carbon, oxygen, silicon, or iron that later generations of stars would produce. They were pure primordial and utterly unlike anything that exists in the universe today. Nobody has ever definitively seen a population 3 star, but theories predict that they were extraordinary objects. Because their gas lacked heavy elements, it cooled differently than the gas that forms stars today. Heavy elements help gas cool efficiently, which allows it to fragment into smaller clumps and form modestly sized stars. Without those heavy elements, the primordial gas clouds could not cool as easily. They stayed hot or collapsed more slowly, And when they finally did form stars, those stars were enormous, potentially hundreds or even thousands of times the mass of our Sun. Some theoretical models suggest they could have been 1,000,000 times more massive. They burned incredibly hot, perhaps 10 times the surface temperature of our Sun, and they were luminous beyond imagination, each one potentially billions of times brighter than our star. But they were short-lived. The biggest ones may have burned through their fuel in just a few million years, a blink of an eye in cosmic terms, before exploding as supernovae, the most violent explosions in the universe. And when they died, something miraculous happened. Deep in their cores, the extreme temperatures and pressures of nuclear fusion had transformed hydrogen and helium into heavier elements: carbon, oxygen, silicon, iron, gold, uranium. All the elements of the periodic table beyond lithium were forged in the hearts and the deaths of stars. When the population 3 stars exploded, they scattered those newly created elements into the surrounding gas, enriching it with the raw materials for the next generation of stars, and eventually for planet's water and life itself. Every atom of carbon in your body was forged in a star. Every atom of oxygen you breathe was created in a stellar furnace and scattered into space by an explosion billions of years ago. The calcium in your bones, the iron in your blood, the gold in a ring on your finger, all of it was born inside a star that lived and died long before our Sun existed. And at the very beginning of that chain, there were the population 3 stars. They were the first forgers, the first creators, the first link in a chain of cosmic chemistry that eventually led to everything. Finding them has been one of the holy grails of astronomy, and Webb was designed with this goal in mind. But finding an individual population, the 3 star, is almost impossibly difficult. These stars existed billions of years ago in the earliest epoch of cosmic history. Their light has been traveling for so long and is so faint that even Webb, with all its power, cannot see a single one of them on its own. To detect them, astronomers need help from the universe itself, and that help comes in the form of gravitational lensing. Gravitational lensing is one of the most beautiful predictions of Einstein's general theory of relativity. When light from a distant object passes near a massive foreground object like a galaxy cluster, the gravity of that foreground object bends the light's path. The effect is similar to looking through a magnifying glass, except the lens is made of gravity rather than glass. If the alignment is just right, the background object can be magnified enormously, sometimes by factors of 10, 100, or even 1,000. It is like adding an extra lens in front of Webb, one made not by human engineers, but by the laws of physics themselves. When Webb points at a massive galaxy cluster and looks through it, the telescope effectively becomes much more powerful, able to see objects that would otherwise be far too faint and far too distant to detect. This technique has already produced some astonishing results. In 2022, Webb followed up on a Hubble discovery of the most distant individual star ever detected, a blue supergiant nicknamed Earendel, whose light has been traveling for 12.9 billion years. Earendel was magnified by a galaxy cluster that happened to be positioned perfectly between it and our telescopes, stretching and amplifying its light until it became visible. Webb was able to determine the star's color and temperature, confirming it as a massive blue supergiant burning at tens of thousands of degrees. It was the most distant single star ever studied in detail, and it demonstrated the extraordinary power of combining Webb's sensitivity with nature's own gravitational telescopes. If the technique works for stars like Earendel, it might also work for population 3 stars, which would be even more massive and luminous. Some astronomers have calculated that a population 3 star near the edge of a massive galaxy cluster's gravitational lens could be magnified by factors of thousands, making it briefly visible to Webb during a phenomenon called acoustic crossing. The chances are slim. The alignment has to be nearly perfect, but with enough observations of enough galaxy clusters, the odds improve. And several teams are actively searching. In late 2025, a team led by Eli Visbol of the University of Toledo announced what may be the strongest evidence yet for population 3 stars, though what they found was not a single star, but a group of them. Using Webb data combined with the natural magnifying effect of a massive galaxy cluster called MAX J0416, located about 4.3 billion light-years from Earth, they studied a tiny faint galaxy called LAP-1b. The light from LAP-1b has been traveling for 13 billion years. That means we are seeing it as it existed just 800 million years after the Big Bang. Without the gravitational lensing from the galaxy cluster, LAP-1b would be far too faint for even Webb to detect. But the cluster's gravity bent and amplified the light, bringing this ancient galaxy into view like a cosmic microscope focusing on a grain of sand. What they found was remarkable. The light from LAP-1b showed clear signatures of helium, but virtually no heavier elements. No oxygen, no carbon, no silicon, just hydrogen and helium and the faintest trace of lithium. This is exactly what you would expect from a galaxy filled with population 3 stars that formed from the pristine gas left over from the Big Bang before any previous generation of stars had lived and died and seeded the cosmos with heavier elements. The stars appeared to be extremely massive and clustered in small groups within dark matter halos, matching theoretical predictions about where and how the first stars should form. The surrounding gas showed minimal metal content, supporting the idea that these stars formed from primordial material that had never been touched by the products of stellar evolution. It is worth pausing here to appreciate what this means. If these really are population 3 stars, we are looking at the very first generation of luminous objects that ever existed in the universe. The first fires, the first light after the cosmic dark ages, the ancestors of every star planet and living thing that has ever existed. We are seeing them as they were 13 billion years ago, frozen in time by the light that has been traveling across the void to reach our telescope. It is one of the most profound observations in the history of science. It is important to note that this finding has not yet been conclusively confirmed. There are other possible explanations for what Webb detected in LAP-1b. It could be unusually pristine clouds of gas rather than actual population 3 stars. Deeper observations will be needed to settle the question. But the discovery has sent a wave of excitement through the astronomical community because it suggests that we may be on the verge of directly observing the very first light that ever shone in the universe. And there is more. In a separate study, astronomers found evidence of population 3 stars in another galaxy, GN Z11, which is one of the most luminous galaxies known at extreme distances. GN Z11 has a special place in the history of astronomy. It was first discovered by the Hubble Space Telescope in 2015, and at the time, it was considered the most distant galaxy ever observed. Its light has a redshift of about 10.6, which means we see it as it was just 430 million years after the Big Bang. That is staggeringly early. The universe at that point was barely 3% of its current age. It was still in its infancy, still emerging from the cosmic dark ages. And yet, GN-Z11 was already there, already shining, already bright enough to be detected across billions of light years. When Webb turned its instruments on GN-Z11, the results were astonishing. A team led by Roberto Maiolino of the University of Cambridge used Webb's near-infrared camera and near-infrared spectrograph to study the galaxy in unprecedented detail. What they found rewrote the narrative of the early universe. GNZ11 was not just a bright galaxy. It was a galaxy in the midst of extraordinary activity. They found signatures of both population 3 stars and a supermassive black hole that was growing at an extraordinary rate, consuming gas, and growing its mass far faster than conventional models allow. The galaxy was doing everything at once, forming stars, feeding a black hole, and producing chemical elements all at a pace that seemed almost frantic. The galaxy also showed an unusual excess of nitrogen. This chemical fingerprint was particularly telling. In modern galaxies, nitrogen and oxygen are produced in roughly predictable ratios by the normal cycle of stellar birth and death. But in GNZ11, there was far more nitrogen relative to oxygen than anyone expected. This excess matches what theoretical models predict would happen if population 3 stars were present. These massive primordial stars would burn through their fuel in specific nuclear reactions that preferentially produce nitrogen, creating exactly the kind of chemical imbalance that Maiolino's team observed. Think about that. In a single galaxy seen less than 500 million years after the Big Bang, scientists found evidence of the first generation of stars ever formed a rapidly growing supermassive black hole and a chemical fingerprint that only the most extreme stellar conditions could produce. It is as if the universe was running through its entire evolution at fast forward in those earliest moments, building complexity at a pace that our models simply did not anticipate. And here is something that makes GNZ11 even more remarkable. It is not just bright. It is unexpectedly bright, far brighter than what our models predict a galaxy of its age and size should be. This excess brightness was one of the original puzzles that led astronomers to question their models of the early universe. The fact that it also contains evidence of population 3 stars and a growing supermassive black hole suggests that all of these phenomena are connected. The first stars. The first black holes and the first galaxies did not develop separately in a neat, orderly sequence. They emerged together, tangled up in a web of cause and effect that is far more complex than the simple picture we had drawn. And this brings us to one of the deepest questions raised by Webb's discoveries. Not a question about galaxies or black holes or dark matter, but a question about the universe itself. A question that goes by a deceptively simple name: the Hubble tension. To understand the Hubble tension, you need to understand one basic fact. The universe is expanding. Every galaxy except those in our immediate neighborhood is moving away from us, carried along by the stretching of space itself. This expansion was first discovered nearly a century ago by Edwin Hubble, who noticed that the farther away a galaxy is, the faster it appears to be receding. The rate of this expansion is described by a single number, called the Hubble constant, and measuring it precisely has been one of the most important goals in all of cosmology. Here is a way to think about it. Imagine you are standing in the middle of a vast field of balloons, and the field is slowly expanding. The balloons nearest to you are barely moving, but the ones farther away are drifting faster, and the ones at the very edge of the field are racing away at tremendous speed. The rate at which this expansion happens, how much faster each additional distance makes the balloons recede, is the Hubble constant. It tells you how quickly the universe is growing at any given moment. Now, the reason the Hubble constant matters so much is that it connects everything else in cosmology. If you know how fast the universe is expanding, you can calculate its age, its size, its future. You can figure out how much dark energy is driving the expansion and how much dark matter is trying to slow it down. The Hubble constant is the heartbeat of the cosmos, and getting it right is essential for understanding virtually everything else. There are two main ways to measure the Hubble constant. The first is to look at the universe as it is today and work outward. Astronomers use a technique called the cosmic distance ladder, a series of increasingly distant objects whose true brightness is known. These objects are called standard candles, and they are one of the most elegant tools in all of astronomy. The idea is simple. If you know how bright a light bulb truly is, and you can measure how bright it appears from where you are standing, you can calculate how far away it is. A 40-watt bulb that looks dim must be far away. The same bulb that looks bright must be close. Standard candles work the same way, except the light bulbs are stars and exploding stars, and the distances are measured in millions of light years. But before you can use standard candles, you need to calibrate them. You need to know how bright they truly are, not just how bright they appear. And that requires an independent measurement of distance to at least a few nearby examples. This is where the very first rung of the cosmic distance ladder comes in, and it uses the simplest method of all. Geometry, specifically a technique called parallax. Hold your thumb up in front of your face and close one eye, then switch eyes. Your thumb appears to shift against the background. The closer your thumb is, the more it shifts. Astronomers do the same thing with nearby stars, except instead of switching eyes, they observe the star from two different positions in Earth's orbit around the Sun, 6 months apart. The slight shift in the star's apparent position against the background of more distant stars allows them to calculate its distance using simple trigonometry. The European Space Agency's Gaia satellite has measured parallax distances for over 1 billion stars, with extraordinary precision, providing the anchor for everything that comes next. The next rung of the ladder uses pulsating stars called Cepheid variables. These stars brighten and dim in a predictable pattern, and the speed of that pattern tells you how bright the star truly is. This relationship was discovered more than a century ago by Henrietta Leavitt, a woman who was working as a human computer at the Harvard College Observatory, cataloguing the brightness of thousands of stars in photographic plates for a salary that was barely enough to live on. Women were not allowed to operate telescopes at the time. They were hired to do the tedious work of measuring and recording stellar brightnesses, a task the male astronomers considered beneath them. But Leavitt saw something in the data that nobody else had noticed. She realized that among a certain class of pulsating stars, the brighter ones pulsed more slowly, and the dimmer ones pulsed more quickly. The relationship was precise and predictable. It meant that if you could measure a Cepheid's pulsation period, you could calculate its true brightness and from that, its distance. It was a cosmic yardstick, and it would become one of the most important tools in the history of astronomy. Leavitt never received the credit she deserved during her lifetime. She died of cancer in 1921, and her contribution was only fully recognized decades later. By comparing a Cepheid's true brightness to how bright it appears from Earth, you can calculate how far away it is. The next rung uses type Ia supernovae, a specific kind of exploding star that always produces roughly the same amount of light. These explosions happen when a white dwarf star, the dense remnant of a dead star about the size of Earth, but with the mass of our Sun, absorbs too much material from a companion star and detonates in a thermonuclear fireball visible across billions of light years. Because they all explode at roughly the same mass, they all produce roughly the same brightness, making them excellent standard candles for measuring the most distant reaches of the universe. Using this method, The best current measurements give a Hubble constant of about 73 kilometers per second per megaparsec. The second way to measure the Hubble constant is to look at the universe as it was in its infancy and calculate forward. This method uses the cosmic microwave background radiation, that ancient afterglow of the Big Bang that we discussed earlier. It is the oldest light in the universe, released 380,000 years after the Big Bang, when the first atoms formed and the cosmic fog cleared. Today, it fills every corner of the sky, a faint whisper of microwave radiation, with a temperature of just 2.7 degrees above absolute zero. It has been stretched and cooled by the expansion of the universe from its original fierce glow into something barely detectable by the most sensitive instruments. But that faint glow is not perfectly uniform. It contains tiny fluctuations in temperature variations of about 1 part in 100,000. These fluctuations are invisible to the naked eye and undetectable by most instruments. But they are there, and they are extraordinarily important. They are the fingerprints of the quantum fluctuations that existed in the earliest moments of the universe, stretched to cosmic scales by inflation, and then amplified by gravity over billions of years. The slightly denser spots where the temperature is a tiny fraction of a degree warmer became galaxy clusters. The slightly less dense spots became the cosmic voids. The pattern of hot and cold spots in the cosmic microwave background is essentially a baby picture of the universe, showing the seeds of all the structure we see today. The European Space Agency's Planck satellite mapped this pattern from 2009 to 2013 with extraordinary precision, measuring the temperature of the cosmic microwave background at millions of points across the sky. The resulting map is one of the most important images in the history of science. By analyzing the sizes, shapes, and distribution of the hot and cold spots, scientists can determine the composition of the early universe with remarkable accuracy. They can figure out how much dark matter is present, how much dark energy, how much ordinary matter, and how fast the universe was expanding at that time. Then, using the lambda CDM model, they can project forward in time, simulating the entire 13.8 billion year history of the universe to predict what the expansion rate should be today. This method gives a Hubble constant of about 67.4 kilometers per second per megaparsec. Those two numbers should agree. They do not. The difference might seem small, about 8%, but in the world of precision cosmology, it is enormous. Both methods have been refined over decades by some of the most careful observers in the history of science. The instruments have gotten better. The data sets have gotten larger. The statistical techniques have gotten more sophisticated. And with every improvement, the two numbers have stayed stubbornly apart. The discrepancy is now at the 5 sigma level, meaning there is less than a 1 in 3 million chance that it is due to random error. This is the same level of statistical significance that physicists required before announcing the discovery of the Higgs boson at the Large Hadron Collider. In other words, the Hubble tension is almost certainly real. It is not a fluke. It is not a mistake. It is a genuine disagreement between two different ways of measuring the same thing, and that is deeply unsettling, because it means one of two things. Either our measurements of the local universe are wrong in some systematic way that nobody has been able to identify despite decades of effort, or our understanding of the early universe, the same understanding that predicts the cosmic microwave background with exquisite accuracy, is missing something. Some piece of physics that we have not yet discovered, some force, some particle, some mechanism that changes the way the universe expands between then and now. What does that mean? It means that either our measurements of the local universe are wrong, Our understanding of the early universe is wrong, or there is something fundamental about the cosmos that we are missing. And the possibilities are tantalizing. Some physicists have proposed that dark energy might not be constant, but could change over time. If dark energy was stronger in the early universe than it is today, it would have caused the universe to expand faster during that period, which could reconcile the two measurements. This idea, called early dark energy, is one of the most actively studied theoretical solutions to the Hubble tension. It would mean that the force driving the expansion of the universe is not a fixed property of space itself, but a dynamic, evolving entity. That would be a revolutionary discovery because the simplest version of dark energy, Einstein's cosmological constant, assumes it never changes. Others have suggested that there may be new particles that we have not yet discovered. Specifically, some theories propose that additional types of neutrinos or other light fast-moving particles existed in the early universe. These particles would have affected the rate of expansion by contributing extra energy to the cosmic mix. If they existed, they could shift the early universe calculation of the Hubble constant upward, bringing it closer to the local measurement. A few researchers have even explored the possibility that we might live in a region of space that is slightly less dense than the cosmic average, a kind of local void. If the matter around us is a bit thinner than the universal average, it would make nearby galaxies appear to be receding faster than they should, inflating our local measurement of the expansion rate. But simulations have shown that the void would have to be implausibly large and empty to account for the full discrepancy, and most cosmologists consider this explanation unlikely. And then there is a newer idea, one that strikes at the very foundation of the distance ladder. Recent studies have suggested that Type Ia supernovae, those supposedly reliable standard candles, might not be as standard as we thought. Research has shown that when you sort supernovae by the age of their host galaxy, you get slightly different results. Supernovae in older galaxies give a different Hubble constant than supernovae in younger galaxies. If the brightness of these explosions depends on the age of the stars that produce them, then the calibration of the entire distance ladder might need to be adjusted. This could bring the local measurement down closer to the cosmic microwave background value, but the data is still too limited to be certain. None of these explanations has gained universal acceptance. The Hubble tension remains one of the biggest unsolved problems in all of physics, and it connects to Webb's discoveries in a very direct way. And this is where Webb's impossible galaxies connect to the bigger picture. The existence of massive galaxies so early in cosmic history puts additional pressure on the lambda CDM model, the same model that predicts the expansion rate of the universe. If our model of how matter assembled in the early universe is off, it could affect the calculations that go into the CMB-based measurement of the Hubble constant. The impossible galaxies do not directly solve the Hubble tension, but they add another crack to a foundation that is already showing signs of strain. Something about our model is incomplete. And here is a thought that connects all of these threads together. What if the same new physics that explains the impossible galaxies also explains the Hubble tension? What if there is a single as yet undiscovered piece of the puzzle that resolves both mysteries at once, that is not as far-fetched as it might sound? If the early universe contained more energy than the lambda CDM model accounts for, whether from dark matter annihilation in dark stars from an early burst of dark energy, or from some entirely new phenomenon, it could simultaneously explain why galaxies formed faster than expected and why the expansion rate seems higher when measured locally. Several theoretical papers have explored this connection, and while none have produced a definitive answer, the fact that these seemingly separate mysteries might be linked is one of the most exciting developments in modern cosmology. This is the kind of moment where science gets truly interesting. Not when everything makes sense, but when nothing quite adds up. When the pieces of the puzzle are all on the table, but they do not fit together the way they should. That is when the real breakthroughs happen. That is when someone looks at the data with fresh eyes and sees a pattern that nobody else noticed. That is when a new theory emerges that explains everything at once, and the scientific community collectively says, "Oh, that is what was going on. We are not there yet, but we are getting closer." And there are even stranger puzzles waiting to be solved. Here is one that keeps cosmologists up at night. There is a star in our own galaxy called HD 1483, informally known as the Methuselah star. Based on its chemical composition and brightness, astronomers have estimated its age at about 14.5 billion years, give or take about 800 million years. The problem is that the universe itself is only 13.8 billion years old. That means this star, sitting right here in our galactic neighborhood, appears to be older than the universe that contains it. Now, the uncertainty in the measurement is large enough that the star's age could be slightly less than the age of the universe, which would resolve the contradiction. But the fact that the two numbers are so close that a single star can come within measurement error of being older than all of creation is itself a sign that something in our accounting might be off. If the Hubble tension is real, and the universe is actually slightly younger than we think, the problem gets worse. And if there are more stars like Methuselah hiding in the data, the tension between stellar ages and cosmic ages could become another crack in the foundation. Here is another puzzle. Webb has found galaxies at extreme distances that contain heavy elements, elements that should not exist yet. Iron, silicon, carbon, elements that require multiple generations of stars to produce. And yet, there they are present in galaxies that existed when the universe was less than 1 billion years old. Some of these galaxies show metallicity levels, the astronomical term for the abundance of elements heavier than hydrogen and helium, that rival galaxies in the much more mature nearby universe. It is as if the chemical evolution of these galaxies was compressed into a fraction of the time that our models predict. The furnaces of the early universe were not just burning. They were running at full blast from the moment they ignited. If you are listening to this and feeling a bit overwhelmed, that is perfectly normal. This is cutting-edge science at its most humbling. The greatest minds in astrophysics are staring at data they do not fully understand, and the universe is refusing to fit neatly into the box we built for it. But there is something beautiful in that confusion, because throughout the history of science, the moments of greatest confusion have always preceded the moments of greatest discovery. Every time we thought we had the universe figured out, it surprised us. And it is surprising us again right now. There is a famous story in the history of physics that is worth telling here. In the late 1800s, many physicists believed that they had essentially figured out the laws of nature. Classical mechanics, thermodynamics, and electromagnetism seemed to explain everything. A prominent physicist reportedly said that all that remained was to fill in the details to measure the constants of nature to a few more decimal places. And then within a few years, two discoveries shattered that confidence completely. Max Planck discovered quantum mechanics. Albert Einstein discovered special relativity. The universe turned out to be fundamentally stranger than anyone had imagined, with particles behaving like waves time, flowing at different rates, depending on your speed, and energy coming in discrete packets, rather than continuous flows. The so-called final details turned out to be doorways to entirely new realms of physics. We may be standing at a similar doorway right now. The impossible galaxies, the little red dots, the Hubble tension. They may be the cracks in our current understanding that lead to the next great revolution in physics. Or they may turn out to have more mundane explanations. We do not know yet. And that uncertainty is not a weakness. It is the very engine that drives science forward. Consider the scale of what Webb has shown us in just a few short years. It found galaxies that should not exist. It discovered a new class of object that may be powered by black holes pretending to be stars. It mapped the invisible scaffolding of dark matter with more detail than ever before. It may have glimpsed the very first stars that ever shone. And it has deepened the mystery about the expansion of the universe that could require entirely new physics to solve. All of this from a single telescope floating in the darkness 1.5 million kilometers from home. Stop and think about that for a moment. A machine built by human hands assembled in clean rooms on the surface of a small rocky planet orbiting an ordinary star in an unremarkable corner of a spiral galaxy is now floating in the void of space and reshaping our understanding of the entire universe. It is one of the most extraordinary achievements in the history of our species, and it is just getting started. But there is one more thing that Webb has revealed, something that does not get as much attention in the headlines, but may be just as important in the long run. It has shown us that the early universe was not the simple, quiet place we imagined. It was chaotic, violent, and creative in ways we never anticipated. Stars formed faster than we thought possible. Black holes grew at rates that defy our equations. Galaxies assembled in record time, and the chemical elements that make up everything we know were forged in furnaces that burned hotter and brighter than our models predicted. There is a concept in science called the principle of mediocrity. It holds that our location in the universe is not special. We are not at the center of anything. Our planet is ordinary. Our star is ordinary. Our galaxy is ordinary. This principle has served science well. It keeps us humble. It prevents us from assuming that we occupy a privileged position. But Webb's discoveries suggest that while our location may not be special, the early universe itself was far more extraordinary than we gave it credit for. It was a time of furious creativity, when the laws of physics were being expressed in ways we had never imagined, building structures and objects that we are only now beginning to see. In early 2025, astronomers using Webb discovered a galaxy they named the Big Wheel, a massive spiral galaxy that existed within the first 2 billion years of the universe. This was surprising because spiral galaxies like our own Milky Way were thought to form gradually through a long, calm process of gas accretion and gentle rotation. The process was supposed to take billions of years. Gas had to settle into a disk, and then the disk had to develop the density waves that create spiral arms, those beautiful pinwheel patterns that we see in galaxies like the Milky Way, the Andromeda Galaxy, and the Whirlpool Galaxy. Galaxies in the early universe were expected to be elliptical with smooth, featureless shapes, because the violent mergers that were common back then should have disrupted any organized structure. When two galaxies collide, the orderly rotation of a spiral disk gets scrambled. Stars get flung in random directions. The beautiful spiral arms get torn apart. But the Big Wheel has a beautiful spiral pattern, clear and distinct, sitting in an era of cosmic history when such structures should have been impossible. The researcher who discovered it, Themia Nanayakara of Swinburne University of Technology, noted that for such a large galaxy, to have spiral structure so early, it must have grown in a very orderly way. Either the mass was assembled without violent mergers, which would be unusual, or the mass was formed within the galaxy itself, born from the gas already present. Either way, it challenges the standard picture. The Big Wheel is a galaxy that followed rules we did not know existed. And then there are the dusty galaxies, another puzzle that Webb has brought into sharp focus. In the standard picture, the very first galaxies should have been almost entirely free of dust. This is because cosmic dust is not the kind of dust you find under your bed. Cosmic dust is made of microscopic grains of solid material silicon, carbon, iron, and other heavy elements that form tiny particles no bigger than the width of a human hair. These elements only form inside stars. In the earliest universe, before many generations of stars had lived and died, there simply should not have been enough heavy elements to produce significant amounts of dust. The first stars would have to form, live their brief lives, explode, as supernovae scatter their heavy elements into the surrounding gas, and then those heavy elements would have to cool and condense into solid grains. The whole process was supposed to take hundreds of millions of years at minimum. But Webb has found galaxies in the early universe that are shrouded in dust, their light reddened and dimmed by clouds of microscopic particles that should not exist yet. One study found galaxies at redshifts beyond 8, meaning we are seeing them less than 700 million years after the Big Bang, that already contain significant dust. This means that stars in the early universe were not only forming faster than expected, they were also dying faster, exploding as supernovae, and scattering their heavy element products into the surrounding gas at a pace that our models never anticipated. The furnaces of the early universe were burning hotter, brighter, and faster than anyone had predicted. And that connects back to the bursty star formation idea we discussed earlier. If galaxies in the early universe went through intense, rapid episodes of star creation, those episodes would also produce intense, rapid episodes of stellar death. Massive stars burn through their fuel quickly. A star 50 times the mass of our Sun might live only a few million years before exploding. If an entire generation of massive stars formed at once in a burst, they would also die, at roughly the same time flooding the galaxy with heavy elements in a sudden wave. That wave of heavy elements could condense into dust far faster than the gradual, steady process our models assumed. It would be like a factory operating at full speed for a short time, rather than trickling along for centuries. Here is something else that is intriguing. Some of the galaxies Webb has observed show unusually elongated shapes stretched out like cosmic sausages rather than the round or disc-shaped forms we see in the nearby universe. These elongated galaxies are not rare. They appear to be common in the earliest epochs of cosmic history, which is puzzling. In the standard cold dark matter model, galaxies should form at the intersection points of dark matter filaments, collapsing into roughly spherical or disc-shaped structures. There is no obvious reason why so many early galaxies should be stretched out like rods. A team of researchers from Arizona State University, MIT, and other institutions compared these elongated shapes to computer simulations of galaxy formation, using different types of dark matter. In the standard cold dark matter model, the simulations could not reproduce the elongated shapes. The galaxies they produced were too round, too compact. But when they used alternative forms of dark matter, so-called warm dark matter or wave dark matter based on exotic particles from theoretical physics, the simulations did a much better job. In these models, the dark matter particles are much lighter and behave more like waves than particles. They create smoother, more elongated filaments in the cosmic web, and galaxies forming along those smooth filaments naturally inherit the elongated shape. Wave dark matter, sometimes called fuzzy dark matter, is a particularly fascinating idea. It proposes that dark matter is made of incredibly light particles, so light that their quantum wave properties become important on astronomical scales. Instead of clumping into dense structures, wave dark matter spreads out into smooth, oscillating patterns. On large scales, it would look almost identical to cold dark matter. But on small scales, the differences would be dramatic, and they might be exactly what we need to explain some of the surprises Webb is finding. This does not prove that dark matter is made of something different than we thought. The evidence is still early, and other explanations for the elongated shapes exist. But it adds to a growing list of observations that are nudging scientists to reconsider some of their most basic assumptions about the invisible substance that makes up most of the mass in the universe. And there is one more discovery worth mentioning before we step back and consider the bigger picture. In late 2025, astronomers studying an extremely distant galaxy called GS 3273, seen about 1 billion years after the Big Bang, found something chemically unusual. The galaxy had an exceptionally high ratio of nitrogen to oxygen in its gas. This might sound like a minor detail, but in astrophysics, chemical ratios are like fingerprints. They tell you what kind of stars lived and died in a galaxy. The nitrogen to oxygen ratio in GS 3273 was so high that no known population of modern stars could explain it. Multiple teams tried to reproduce the signature using different models, including rapidly rotating stars, massive explosions, and the early stages of globular cluster formation. None of them worked. The only explanation that fit was population 3 stars. The unique nitrogen abundance could only be produced through the evolutionary phases of the most massive, most primordial stars burning quickly enough to produce and release an excess of nitrogen, while other elements stayed at lower levels. It was a chemical ghost, a signature left behind by stars that died billions of years ago. This finding connects to the LAP-1b discovery. While LAP-1b provides evidence of population 3 stars through their formation environment, GS 3273 provides evidence through their chemical fingerprints, 2 independent lines of evidence pointing toward the same conclusion. The first stars are beginning to emerge from the data. The early universe that Webb is revealing is more complex, more active, and more surprising than the one we drew on our whiteboards. And every new observation seems to widen the gap between what we expected and what we actually see. So where does that leave us? It leaves us in one of the most exciting moments in the history of astronomy. We are standing at the edge of a new understanding of the cosmos, one that may require us to rewrite some of the chapters we thought were finished. The impossible galaxies may not be impossible at all. They may simply be telling us that the universe found ways to build structures faster and more efficiently than we gave it credit for. The little red dots may be the missing link between the dark ages and the galaxies we see today. The Hubble tension may point us toward new physics that will transform our understanding of space-time and energy. And the population 3 stars, those first flames in the cosmic darkness, may finally be within our grasp. For the first time in human history, we have a telescope that can see them. Not clearly, not yet. But the light is there, faint and ancient, waiting to be read. Every spectrum from a distant galaxy is a treasure map, and somewhere in that data, the fingerprints of the very first stars are waiting to be decoded. The search is no longer theoretical, it is observational. And that is a profound shift. There is a question that people often ask when they hear about discoveries like these. What does it matter? Why should we care about galaxies that are billions of light years away, about stars that died before our solar system existed, about the expansion rate of a universe that we will never travel across? It is a fair question, and it deserves an honest answer. It matters because these discoveries tell us who we are. Not in a sentimental way, but in a literal physical chemical way. The atoms in your body were forged in stars that lived and died billions of years ago. The iron in your blood was created in a supernova explosion. The oxygen you breathe was manufactured in the core of a star that no longer exists. You are, in the most literal sense, made of star stuff. And the population 3 stars, those first giants that Webb may now be glimpsing, are the beginning of the chain that leads to you. Understanding them is understanding our own origin story, written not in words, but in atoms. It also matters because the Hubble tension, the impossible galaxies, and the mysteries of dark matter, if you can't sleep, it's not because you're not tired. It's because your mind is still running, replaying the day, looping through the week, landing on something from years ago that has no business keeping you awake. Or you fall asleep fine and wake up at 3 a.m., wide awake. And now you're lying there doing the math on how many hours you have left before the alarm goes off. White noise doesn't fix that. Sleep playlists loop every few minutes and pull you back right when you were drifting. Meditation apps ask you to try. And trying is the problem. Your mind doesn't need to be quieted. It needs somewhere to go. Beyond the Stars is a full collection of long-form narrated space journeys built for a mind that won't stop on its own. Not music, not ambient noise. Calm, steady narration. Slow pacing. Deep space. Something your mind can follow without thinking. Something continuous enough that the looping just runs out of room. You're drifting through distant star systems, moving past quiet worlds, floating so far from everything that whatever was running in your head gradually loses its grip, without you forcing it. 5 overnight journeys, each one 6 to 8 hours long. No ads, no endings, no sudden sounds at 2 a.m. One purchase, any device. Lifetime access. A sleep app costs you every single month, and it still interrupts you. This is $39 once, and it works while you sleep, not while you're trying to. If you're watching this channel, you already know what this kind of content does to a restless mind. Click the link below. Get beyond the stars tonight, and actually sleep. Could lead to new physics that transforms our technology and our understanding of reality. Every major revolution in physics has eventually led to practical applications that nobody could have predicted at the time. Quantum mechanics gave us transistors, lasers, and the entire digital revolution. General relativity gave us GPS satellites and gravitational wave detectors. We have no idea what the next revolution will bring. But if history is any guide, it will be something that changes the world in ways we cannot imagine. If you are enjoying this journey through the universe, take a moment to subscribe to this channel and turn on notifications so you never miss an exploration like this one. What Webb has taught us above all else is humility. We built this telescope to confirm our theories, and instead it challenged them. We pointed it at the edge of time expecting to see infancy, and instead we found maturity. We thought we knew the story of the universe, and it turns out we were missing some of the most important pages. But that is not a failure. That is exactly how science is supposed to work. Every great discovery begins with something that does not make sense, an observation that refuses to fit a number that will not balance a galaxy that should not be there. The universe is not broken. Our understanding of it is simply incomplete. And thanks to Webb, we now know where the gaps are. In the years ahead, new telescopes and surveys will build on Webb's discoveries. The Euclid Space Telescope, launched by the European Space Agency in 2023, is already mapping the distribution of dark matter and dark energy across a far wider section of the sky than Webb can cover. while Webb excels at looking deeply at small patches of sky. Euclid is designed for breadth surveying vast swaths of the cosmos to understand the large-scale distribution of invisible matter. The two telescopes complement each other perfectly, like a microscope and a wide-angle camera working in tandem. NASA's Nancy Grace Roman Space Telescope, set to launch, soon will provide another crucial piece of the puzzle. Roman will have a field of view 100 times wider than Webb's, allowing it to survey enormous areas of the sky while still detecting faint distant objects. It will apply the same weak gravitational lensing technique that produced the Cosmos Webb dark matter map, but over an area thousands of times larger. The result will be a three-dimensional map of dark matter distribution that covers a significant fraction of the observable universe. If there are anomalies in how dark matter behaves at large scales, Roman will find them. And the Vera C. Rubin Observatory in Chile, which began operations in 2025, will survey the entire southern sky with unprecedented speed and depth. Over its 10-year mission, it will catalogue billions of galaxies and map the cosmic web on the largest scales ever measured. It will detect millions of supernovae, providing new data that could help resolve the Hubble tension. And it will track the way galaxies cluster together over time, testing whether the Lambda CDM model's predictions hold up as the data gets better and better. Together, these instruments will give us a view of the universe that is broader, deeper, and more detailed than anything we have ever had. They will help us test the theories that Webb has shaken. They will reveal whether dark matter behaves the way we think it does. They will tell us whether the Hubble tension is a sign of new physics or a measurement problem we have not yet solved. And they will bring us closer to understanding the very first moments of cosmic history, when the darkness gave way to light, and the universe began its long, strange, magnificent journey toward everything we see today. There is a pattern in the history of science that is worth remembering here. Every time we build a better instrument for looking at the universe, we discover things we did not expect. When Galileo first pointed a telescope at the sky, in 1609, he found mountains on the moons around Jupiter and phases of Venus. None of these were predicted by any theory of the time. When Hubble first measured the distances to faraway galaxies in the 1920s, he discovered that the universe was expanding, a finding so unexpected that even Einstein refused to believe it at first. When astronomers first mapped the cosmic microwave background with the COBE satellite in 1992, they found the seeds of all the structure we see today, tiny fluctuations in temperature that would grow into the galaxies and galaxy clusters that fill the cosmos. And now with Webb, the pattern continues. We built the most powerful telescope in history, pointed it at the edge of time, and found a universe that is stranger, more creative, and more beautiful than we ever imagined. But for now, the James Webb Space Telescope floats in the silence of deep space, its golden mirror catching light that has been traveling since before the Earth existed. It sees what we cannot see. It hears what the universe has been trying to tell us for 13 billion years. And what it is telling us is this: we have only just begun. Think about what it means to look at the night sky and know that most of what you are seeing is not what is actually there. The stars you see are a tiny fraction of the stars that exist. The galaxies visible to the naked eye are a handful out of 2 trillion. And even those 2 trillion galaxies, with all their hundreds of billions of stars, make up only about 5% of everything in the universe. The rest is invisible. Dark matter, dark energy forces, and substances that we can detect, but cannot explain. We are surrounded by mystery on every side, and it took building the most complex telescope in human history to even begin to see the outline of what we do not know. The cosmos is bigger, stranger, and more beautiful than we imagined. The galaxies that should not exist are real. The black hole stars that defy classification may be the key to understanding how everything began. The dark matter that holds the universe together is woven into every structure we can see and countless structures we cannot. The first stars that ever shone may have left their fingerprints in the light that reaches us today. And the universe itself is expanding in a way we cannot fully explain, hinting at forces and phenomena that lie beyond the reach of our current understanding. There is a certain kind of beauty in not knowing, in standing at the edge of the known and peering into the darkness beyond. Every great discovery in the history of science started with a question that had no answer, an observation that did not fit a piece of data that refused to behave. The impossible galaxies are that kind of observation. They are an invitation to think bigger, to imagine more boldly, to accept that the universe is under no obligation to make sense to us, at least not yet. We are living in a time of cosmic revelation. Every image Webb sends back to Earth is a page from a story that has never been told before. Every spectrum, every photon, every tiny red dot in the ancient darkness carries information that could rewrite our understanding of reality itself. And the pace of discovery is only accelerating. In the next few years, Webb will turn its golden eye toward even more distant targets, peering deeper into the cosmic dark ages, searching for more population 3 candidates, hunting for more little red dots, and testing the boundaries of our theories with every new observation. Some of those observations will confirm what we already believe. Some will surprise us in ways we can predict. But the most important discoveries, the ones that change everything, are always the ones nobody sees coming. That is the nature of exploration. You build the ship, you set the course, and then the ocean shows you something you never imagined. And the most remarkable thing of all is that we are here to witness it. In a universe that is 13.8 billion years old, spanning 93 billion light years from edge to edge, filled with 2 trillion galaxies and more stars than grains of sand on every beach on Earth, we are the ones who built the telescope. We are the ones who unfolded it in the darkness. We are the ones who pointed it at the edge of time and asked the simplest, most profound question a conscious being can ask. What is out there? We asked, and the universe answered, not with a simple reply, but with a cascade of mysteries that make the question even deeper than it was before. The impossible galaxies, the little red dots, the black hole stars, the cosmic web of dark matter, the first light, the Hubble tension. Each answer leads to 10 more questions, and each question pulls us further into the unknown. But that is not a cause for frustration. That is a cause for wonder. Because every question we cannot yet answer is proof that the universe is richer than our imagination. Every mystery is a doorway. Every puzzle is an invitation. And every time we think we have reached the end of the story, we discover that there are chapters we never knew existed. The universe is not done with us, and we are not done with it. The James Webb Space Telescope is still out there, still watching, still listening, still catching the light of ancient fires that burned before the Earth was born. And somewhere in that light, in the faint glow of a tiny red dot, or the spectral fingerprint of a primordial star, there may be an answer that changes everything we think we know. That is the promise of science. Not certainty, but the endless, exhilarating pursuit of understanding. Not a destination, but a journey. And right now, at this moment in history, that journey has never been more exciting. Think about where we started and where we have arrived. We began with a telescope folded up inside a rocket on a launch pad in South America. We watched it unfold in the darkness of space, its golden mirror catching the first photons of ancient starlight. And from those photons we learned that the universe is not what we expected. Galaxies formed faster than we thought. Black holes grew larger than we imagined. New classes of objects lurk in the ancient darkness, defying categorization. The invisible scaffolding of dark matter holds everything together in a web of filaments and clusters that mirrors the deepest patterns of nature. The first stars that ever shone may have left their traces in the light that reaches us across 13 billion years. And the very fabric of space is expanding at a rate that two of our best measurement methods cannot agree on, hinting at physics we have not yet discovered. Each of these discoveries alone would be enough to define a generation of astronomy. Taken together, they represent one of the most transformative periods in the history of science. And we are living through it right now in real time as the data streams in from a telescope that is still barely into its mission. Webb was designed to operate for at least 5 years, but its fuel efficiency during launch was so good that it may last 20 years or more. That means the best discoveries may still be ahead of us. The deepest images have not yet been taken. The most distant galaxies have not yet been found. The most surprising spectra have not yet been analyzed. Whatever Webb has shown us so far is only the prologue. And there is one more implication of all this that is worth sitting with for a moment. If the early universe was more active, more creative, and more chemically complex than we thought, it means the conditions for life may have arisen earlier than we assumed. Life as we know it requires heavy elements. Carbon for organic molecules, oxygen for water, iron for the hemoglobin that carries oxygen through your blood, phosphorus for DNA. If these elements were being produced in abundance just a few 100 million years after the Big Bang seeded into the cosmos by explosive population 3 stars and the furious star formation episodes of the earliest galaxies, then the raw materials for life were available far earlier in cosmic history than we previously believed. That does not mean life existed that early. The conditions need to be right, and we have no evidence one way or the other. But it means the window of possibility is wider than we thought. The universe may have been ready for life long before anyone imagined. This is perhaps the deepest implication of Webb's discoveries. Not just that our models of galaxy formation need updating. Not just that dark matter and dark energy are more mysterious than we thought, but that the story of the universe is at its core the story of complexity emerging from simplicity. Hydrogen and helium becoming stars, stars becoming heavy elements becoming planets, planets becoming oceans, oceans becoming chemistry, chemistry becoming biology, biology becoming consciousness, and consciousness building a telescope and pointing it back at the beginning, trying to understand how it all started. We are the universe looking at itself, and thanks to Webb, we are seeing things we have never seen before. The answer is still being written. The universe is not done surprising us, and neither is the James Webb Space Telescope. Thank you for joining me on this journey through the cosmos. If this video made you think, made you wonder, or made you see the night sky a little differently, please like this video and share it with someone who looks up at the stars and asks the same questions we all do. Subscribe to this channel for more explorations of the universe, and leave a comment below telling me which discovery from Webb has amazed you the most. I read every single one, and your curiosity is what makes this channel possible. Until next time, keep looking up. The universe has more to show us than we ever dreamed.